today we are going to be talking about muscle, specifically skeletal muscle, and all the stuff that goes along with that. So, first of all, muscle always has to do with calcium. So a muscle cell is the same thing as a muscle fiber. They're synonymous with each other. So we're going to look at some of the things. So first of all, we're going to take a look at our sarcomere here. We've got our Z disc, and then we've got our myosin, also known as titin, and then we have our actin, which is also known as nebulin. And see, there's our myosin with our myosin heads on there, and then this middle line where they don't touch is the M line. Then we have these little myosin heads. This is them blown up a little bit, the tail, the neck and hinge region where they bend back and forth, and then we have the head enzyme, the ATPase. Okay, so now we're going to get into how this lovely process works. So first of all, this is our presynaptic neuron, and we've got action potentials coming down, and you've got all your vesicles with the neurotransmitters in them. In order for these to exocytose, like shown here, we have to have calcium come in through that voltage-gated calcium channel. And it comes and it binds the snare proteins to those vesicles so that they can release all of their neurotransmitter. A lot of the time, this neurotransmitter, like we've learned in previous videos, is going to be ACH. And we have acetylcholinesterase, which is what comes and eats those. Now, for the postsynaptic area of our story, we've got different protein channels. Now, the one that's most important for this discussion is going to be our sodium, our voltage-gated, or ligand-gated sodium channel, Because what this neurotransmitter comes in and does, it comes in and it binds to that ligand-gated channel, and it opens it so that sodium can rush in. This sodium rushes in, and its job is to come up here and to bump and nudge and say, hey, we want the rest of our buddies in here. And so the rest of the sodium can all come in. We've got two other channels that are important to this process. We've got our potassium channel and then our voltage-gated calcium channel over on this side. And these help maintain the equilibrium of charges in between the extracellular fluid and the intracellular fluid. So what happens is you get all these sodiums piling into the intracellular part of our cell, and they come and they line, that positive charge lines up on the outside, and these channels are found all around. So these positives then come down and they start pushing on what's called our DHP. Our DHP is a voltage-gated channel, And when that happens, it causes a conformational shift, which then activates our ryanodine receptor right here. And this ryanodine receptor opens and allows calcium from the SR to be released. Now this calcium is going to come out, and since both of these are open, you might say, hey, it's going to want to come to the ECF. Well, it does, but you've got a driving force of calcium from the outside, the ECF, also pushing in. So what happens is that driving force of that pushes the calcium that's coming out of here down. And it has two different routes that it can go. So the first one is it can go and be reuptaken in our circuit pumps, and it just filters back in. But this is a very expensive process because this is moving it against its concentration gradient, requiring ATP. So then we have our other option where the calcium can come down, and this is where we go back to kind of what we were talking about with muscles that we have going on. So it comes and binds to what we call troponin. Now, our little way to remember this is I think of troponin as being the creepy carnival worker that has to come push the button for the ride to work. And then the tropomyosin, which is this bar-like thing blocking the G-actin, that's like the bar that comes down on a roller coaster and keeps you stuck in there. And then we are like the G-actin, the ones we want to get on. So anyway, so the calcium comes and it pushes the button on our troponin, and then that releases the tropomyosin. So the tropomyosin can then flip up allowing access to the G-actin. And these G-actins have myosin binding sites on them. And this is then where we will move to our next process, but where the myosin heads can start to contract and power stroke and do their work. This whole thing is called F-actin. And there's 3 different troponin parts that we need to know about. There's troponin T, troponin I, and troponin C. Now, there's 4 different binding sites on this. 2 of them are low affinity and 2 of them are high affinity. And we know that there's 7 G-actin places or spots that are covered up by our per 1 tropomyosin. And then for every tropomyosin, we have a troponin that attaches. And this leads us to our next little section. Oh, but before I forget, there's another little sneaky part of this process that's important, and that's our chloride channels. And these come in and they also help regulate the system. Okay, back to the next part that we want to talk about. So this is our cross bridge cycle. This is how we contract our muscles. And this whole process happens 5 times a second, which is pretty impressive. So we're going to start with step 1. Step 1, we have ADP and a phosphate in the cocked position. Now, it's not attached to our actin yet. It's just sitting there cocked. Now, what happens next is you have an inflow of calcium, and that comes in, and calcium decapitates the phosphate, and it causes this to be bound to the actin side, or the actin to the ATP head. And that binding causes heat to be released. Now what happens is we have our ADP and our phosphate, that energy has been used up in this process, and they leave. And this is called the power stroke. Now we kind of have this lonely poor guy down here. This is the uncocked position. So our myosin head doesn't have any ADP in it, and because it doesn't have the phosphate, it's now not at the right angle that we originally had because the phosphate's not taking up that space. So this is our relaxed area. Now, when ATP is added, that goes into that myosin head, and it still is uncocked because we don't have that phosphate out there yet. So this takes place, and this will cause heat also to be released, creating that, putting that ATP in the myosin head. And so then our next step is we have hydrolysis, which cleaves one of those one of the phosphates on the ATP because it's adenosine triphosphate. And so now we have adenosine diphosphate, and then that extra phosphate is now in its place. So we went from uncocked to cocked back up here. Also important is a little step that also occurs here. So we also have a calcium that is spit out here, the calcium that we had over here that was being used. This is the step where it's kicked out, and this is known as the relaxation. So this calcium gets recycled again, which is pretty dang cool. So it goes from being a part of the cross bridge cycle, which is actually happening over here, and it comes back and it is also re-uptaken into the SR. So it's all being recycled, which is pretty amazing. Okay, so we have some different types of energy that we use to make this process go and to provide energy for us to create the contraction. So we have cytosolic ATP, which lasts about 5 seconds, and that's from the cytosol. And then number 2, we have creatine phosphate, and there's 2 different types of ATP that we can get. We can get the ADP plus the phosphate, or we can get the ADP plus the creatine phosphate. And that lasts a little bit longer. That lasts about 10 seconds. And then our third option is glycolysis, which is glycogen minus glucose leading to ATP, and that lasts about 60 seconds. And then our last one is aerobic respiration, which can last several hours. So that one's pretty amazing, but this one is the most common. Okie dokie, so we're gonna jump ship and come to this other section up top. This is a diagram of a whole muscle. So we start with a myofibril and see there's our myosin with our myosin heads coming out here. Then we come to our muscle fiber or our muscle cell. And then a bunch of those become several different areas. We've got our endomysium, which is on the inside, and then our paramysium, which is kind of the outside of that. And then our next layer is the epimysium. And that all is considered fascia. So from the outside to the inside, you have the epimysium, then the paramysium, then the endomysium, then the sarcolemma, then the myofibril, which interestingly makes 80% of intracellular space. And then you have number 6 is the myofilament, which is where our contraction takes place. And then 7 is the sarcomeres, which, yeah. Okay, so increased sarcomeres equal hypertrophy. An increased number of muscle cells also equals hypertrophy. So those both affect that. So skeletal muscle fibers, there's 2 different types. We have slow twitch oxidative, which is type 1, and then we have our second, which is fast twitch oxidative, and this is a type 2 through glycolysis, excuse me. And there's several different characteristics of these. So first of all, myosin atipase. What is it in these different types? So type for a slow, or also known as aerobic twitch oxidative, is type 1, like we said, and then our fast is aerobic, and which means it requires oxygen, is a type 2A, and then we have fast twitch anaerobic, which is 2X, so it does not like oxygen. Then we have the size to consider. So slow twitch is small, fast twitch aerobic is medium, and anaerobic is large. And our blood supply to our slow twitch is extensive. Whereas with our fast twitch, aerobic is medium, and then our anaerobic is small. So blood supply is also a characteristic in which the slow aerobic is red, the fast aerobic is red but slightly less red, and then our anaerobic is going to be white. So if you think about like a chicken breast, the chicken breast is really white, but then the chicken legs are dark. And so those are the different colors of these types. And then we have our power profile. For slow, it's low. And then for fast, it's high. And then for anaerobic fast, it's the highest. Fatigue, you don't fatigue with slow muscles. You got lots of blood supply that is going to that area, providing energy. And whereas with fast aerobic, you have medium amount of fatigue. And then with anaerobic fast, you have very fast fatigue. That's a very strong, quick action that you can't sustain very long. And then our energy source for slow aerobic is oxidative, and that's the same for fast aerobic. They're both oxidative. They like oxygen. And then anaerobic can't get it from oxygen because it doesn't like it, so it's going to go through the glycolytic. Okay, so we have different types of fatigue. So fatigue is when the brain sends signals to muscles and the muscles don't respond. So we have 2 different types. We have psychological and physiological, which psychological is central, which means it's psychological is where you first show fatigue. But physiological actually is the real fatigue that lasts a lot, that really means if your body's tired and worn out. So you have 2 different types of physiological, and that's low frequency and high frequency. So low frequency has mostly to do with calcium, and high frequency has to do with membranes. So we're going to jump down here and go a little bit more in depth. So low frequency is going to last 24 to 27 hours, which is a pretty decent time, and it is from calcium release. Whereas high frequency is impaired membrane excitability, and also can be sodium-potassium pumps. And this is super short. It lasts 30 seconds to 30 minutes, so you can replenish high frequency a lot quicker. And different things that contribute to fatigue are an accumulation of inorganic phosphates, and we have hydrogen ion accumulation and pH change, and glycogen depletion, imbalance in potassium, and ATP shortage. And that can kind of be shown here. If we don't have enough ATP, then we can't power these circa pumps, and so then we can't be pushing calcium, which causes this whole process to stop because you lose the calcium that's binded to the troponin, making it so the tropomyosin comes back down and covers those heads, and you can't have a contraction because then the myosin heads can't come bind to the G-actin. So, and this also can be affected too, is if you have a buildup of calcium or a buildup of potassium or anything outside, or if you have a chloride channel that stops working and stops equalizing all of those charges out, you're gonna make it so that this all becomes blocked, which is going to throw off the balance, and then you don't have these positive charges that want to come in, and the whole process once again stops up. So for fainting goats, like we learned in class, they don't have a chloride channel. So when they get a lot of stimulus coming in, or they get freaked out, all of this takes place, but then it gets built up because there's no equilibrium happening there, and they faint. So, okay, we will see you shortly for our next section of this video. Okay, now we're to smooth muscles. So first we're going to talk about a few things that is important to know with smooth muscle. So smooth muscles are slower than skeletal muscles. There's more force per unit. They're shorter, or they shorten 80% of their length, which is pretty fantastic. They're fatigue resistant. So we talked about sphincters are smooth muscle, and they need to be able to contract a long time, or you're going to have a lot of embarrassing situations. Myofilaments 10,000 times longer than their diameter, and then they contract as a single unit. They can work independent of the nervous system, and most importantly, they remain in a tetanic state without fatiguing, which is pretty cool, like we talked about with the sphincters. So there's two types. There is rhythmic and sustained. Rhythmic is your phasic, and sustained is your tonic. And both of those, the contraction begins with phosphorylation of the myosin light chain. So with our skeletal muscles, troponin and tropomyosin regulate when the myosin head can bind to actin, whereas with smooth muscle, it lacks troponin. So it requires an increase in intracellular stores of calcium and stores of calcium in the SR that are regulated by ryanodine in order to regulate that contraction that we talked about earlier in skeletal muscle. So calcium-induced calcium release is where IP3 binds to the SR, making it so that calcium is released, and then that binds to the ryanodine on the SR to release more calcium. And that leads to the activation of MLK that we're going to talk about here shortly. So voluntary muscle control, so you've got two different types. You've got upper motor neurons and lower motor neurons. And upper motor neurons are in the cerebral cortex. And so you've got a lot of planning, initiation, and coordination. Whereas with the lower motor neurons, they leave the spinal cord and synapse with skeletal muscle. So this is a single nerve system that's a somatic nervous system. So we've got several different reflexes. So first of all, we have our receptors, which we have 5 different types of receptors that we're going to talk about. We've got mechanoreceptors, and those are initiated by like touch or pressure. Chemoreceptors are chemicals that trigger that, and then thermoreceptors are triggered by temperature. Photoreceptors, light, and nociceptors are pain. And then you have afferent or sensory neurons, and then you have the control center where all the action happens and things are decided. And then efferent is away from, and then you have the effector, which is the action that takes place. So let's get into the fun stuff. So we have smooth muscle has phasic and tonic options to choose between. So let's start with phasic. So first of all, just like our other skeletal muscle diagram that we drew earlier of contraction, you've got your ADP and your phosphate head. And previously we just added calcium in to make this reaction happen, but for phasic we also add in ATP, which then allows MLK to come in as well. And let's jump to MLK right now, actually. So this is MLK in its inactive state, and then you have calmodulin. And when it's in the inactive state, it can't let anything in. It can't turn phosphate into ADP and phosphorus. So this ADP comes in, but it wouldn't be able to separate out for the next process that we need. So MLK makes it possible for the ADP to do, or ATP to do its job. So that calmodulin comes in and it binds, and then we got all that calcium. So let's keep going with our steps. So that comes in, allowing this to create a bond to the actin, releasing heat, just like last time, except this time you can see that we've got an extra phosphate in there. So then, just like before, we kind of decapitate one. And so we lose that phosphate and we lose our ADP. However, we still have that other phosphorus stuck there. So at this point in the cycle, we don't have anything in our myosin head, but we still do have a phosphate attached. So then when we go to add ATP, this flips over to this side and our ATP binds. Now this has two different ways that it can go. You can either have hydrolysis and rebinding, so it skips this step, or you have hydrolysis and your MLCP comes in, getting rid of your phosphate. So if you are to skip and rebind, you just go to this point where you add another phosphorus, and it's the hydrolysis part is where it cleaves that ATP to ADP, and that's how we get that phosphate. Or the hydrolysis and MLCP, we're going to come over to that. This is the inactive form of it, so it's where it has a phosphate attached to it, and that is brought about by Rho kinase. Rho kinase comes over and you throw in an ATP with it, and you get that phosphate. Now the active form of MLCP does not have the Rho kinase doing its job, and so you don't have the phosphate either. So anyways, it comes in, it breaks off the phosphate. So that's what we have going on right here, is it comes in, breaks off the phosphate, and then the hydrolysis causes the ATP to give its phosphorus, and you've got your ADP again. The whole cycle can continue. Okay, now for tonic, it's a little bit different. Our first step is pretty well the same. We have our MLCK that comes in. When the phosphorus is added, though, the tropomyosin just moves. So then this is where it gets a little different. So we get our phosphorus kicked off, we get our ADP kicked off, but then we want to get rid of that extra phosphate that we have. So MLCP comes in and breaks that off and removes that. So now you're back to just an uncocked myosin head, excuse me. Then when we try to put our ATP in, this causes what is called the latch state. I've got the hiccups. Excuse me. And so it takes forever for ATP to enter the myosin head and to bind, and so sorry, hiccups. It takes forever for this to attach, and that's where we get our latch state or our lagging phase. Okay, so here's kind of what happens in the graph form of that. So phasic, we've got our enzyme activity going this way and our time going this way, so it's nice and slow and steady, and you've got a large difference, and that's MLCK, MLCP, and then the calcium. And then with tonic, it's a lot greater of a curvature and a lot quicker. Okay, this is a smooth muscle cell. So we're going to talk about a little bit what's going on the inside. So we know that we've got, this is the SR. You know that we've got a bunch of calcium in the SR compared to the inside of the cell. So we have some things that we need to establish first. So you have your sodium-potassium pump, or this is actually a sodium-calcium pump, maintaining equilibrium and our concentration gradients. You have Circa pumps, which we know are super important for bringing calcium back into the cell. And then you have pumps bringing it out of the cell. But what's really important here is your G protein that you've got right there. So the G protein, the alpha subunit, is kicked off when you have something that binds to it. And this is our calcium phospholipase C. And this releases IP3, which then comes into the SR, which then kicks out that calcium. So we need to depolarize the channel in order to open it. So this then can come, and we've got our voltage-gated calcium that causes calcium to be brought back into the cell. We've got a stretch-activated calcium channel that brings calcium into the cell. So we're working on getting calcium out of the cell or out of the SR and into the cell so it can go do its job. And we're back. So first of all, we're going to start with our brain and some of our muscles. Now we have 3 different motor units that are sending signals back and forth between the brain and the muscle. Our first one is the alpha motor unit, and this is where the brain sends signals back to the muscles that it innervates. Now, when these muscles are stretched, for instance, the muscle spindles are these things right here, and they sense that stretch and they go, hey, we're a little uncomfortable with change here, knock it off. So they then send signals through the sensory neuron back to the brain so that the brain can be like, okay, we're stretching too much, let's contract these muscles to save them. And so that is our gamma motor unit that comes back to the spindle fibers saying, hey, contract. So we're going to jump over here and talk about our stretch receptors a little bit. And we've got a nuclear chain fiber, which is the green. And then we've got the bag fiber, which is in red. Obviously, the bag fiber is bag-like. So with our nuclear chain fiber, we have a static gamma motor neuron that brings information in. And then that information is then set off. And this has to do with duration and duration information, and that's type 2. And then for our bag fiber, we have, instead of static, we have dynamic gamma motor neurons, and this signal gets thrown around the bag and then out as a type 1A, and this has to do with rate information. Okay, now for the exciting part. So for our scenario, we are going to be using the leg. As you can tell, that's a lovely leg. And we have our agonist and our antagonist muscle. So our agonist is where the muscle that is being contracted and is kind of the one that we're focusing on. And then the antagonist is its opposite reaction muscle. So we've got our leg, and then we've got our lovely spinal cord right there. So first of all, let's say we were to stretch our antagonist muscle. This stretch, like we've talked about earlier, gets sensed by the muscle spindle, and that sends information back to the brain through our alpha motor unit. And this is also known as an EPSP, or an excitatory postsynaptic potential. And so it has 2 different things that it affects. So our first root is going to be our antagonist muscle, sensory neuron. Not sensory neuron, gamma motor unit. So this comes and tells the antagonist muscle to contract. Whereas on this side, we have an IPSP, which is an inhibitory postsynaptic potential. And this comes in and inhibits the antagonist muscle. So it comes down, tells this one, hey, Joe. Okay, so now we've stretched our muscle. Now we're telling it to contract because we don't like to stretch. And this causes then our Golgi tendon reflex. Now, let's clarify that. The Golgi tendon reflex doesn't activate with stress, but with stretch, but with tension. So when you have tension on that tendon, that's when you get your signal. So then that lets you know, hey, we're a little too overstretchy. And it comes, and there's two different pathways with this one that it's going to affect. So for the antagonist muscle, it's going to come down here and it's going to turn off the antagonist. Whereas with our agonist muscle, it's going to come in here with an inhibitory postsynaptic potential and affect that agonist muscle that then goes there. Okay, so we're going to really quickly talk about our different senses. So we have sight, sound, touch, taste, and smell. Sight, the stimulus is the photon, so the receptors are photoreceptors. For sound, it's pressure waves, and then you have mechanoreceptors, which are stimulated by pressure or touch, and we already know that about mechanoreceptors. So for touch, the stimulus is pressure, and that's also going to be a mechanoreceptor. For taste and smell, it's both stimulated by chemicals, which then means we're going to have chemoreceptors. So let's start with taste. For taste, there are 3 different things that we have to know that affect how things taste. So you've got many different receptors that like different things. And then you have smell, which affects how things taste. That's when you get sick and have a cold, you can't taste things very well. And then the third is that other sensory receptors are in the mouth too. So that's going to be your texture. So we've got lingual papillae, and this is where the taste buds are. So there's 4 different types. You have circumvallate papillae. You have fungiform papillae, which are mushroom shaped. You have I cannot speak tonight. Folate papillae, which are leaf shaped, and filiform papillae, which are string shaped. And these top 3 contain taste buds, and there are about 50 to 150 receptor cells in each of these taste buds. So the 3 nerves that contribute to this are the facial nerve, the glossopharyngeal nerve, and the vagus nerve. And so the different tastes that we can taste are salt, sour, sweet, bitter, and umami. So salt is, you're going to be accepting ions, which most of the time the most common is sodium. And then for sour, that's for acids, so hydrogen. And then for sweet, it's carbs. Bitter are anions, and then umami it's glutamate. So this is kind of what a tongue looks like blown up. So we've got our vesicles, and then we have our taste buds, which are 125 cells. Isn't that crazy? So here are our examples of our 3 different types. So the first one is salt, and you've got an EMP an ENAC or an ENaC receptor that is going to allow sodium to flow in, depolarizing the cell. And each of these bottom half of our examples are the same. So you've got your SR, and then you've got your vesicles and your voltage-gated calcium channels. So this comes in depolarizing the cell, causing an action potential. Same thing, you've got an ENaC, except this time it's hydrogen for sour. And then for sweet, bitter, and umami, you've got a G protein that sends off its alpha subunit to start up phospholipase C. And then that lets in different cations to start an action potential. So next we're going to jump down to smell. Olfactory receptors activate adenylyl cyclase, which then adenylyl cyclase produces cyclic AMP, which then opens cation channels, which then sodium and calcium are now allowed to enter the cell because of the cation channel. And then these coming in depolarize the cell, causing an action potential. So here we have a lovely little nose, and we've got these receptors connecting through the cribriform plate to the olfactory bulb. And this is kind of what they look like blown up. So you've got a G protein that sends off its alpha subunit to activate adenylyl cyclase right there. And adenylyl cyclase is going to send off cyclic AMP, and that comes over and it opens the calcium and sodium channel. It's an ion channel. And then that then causes this chloride channel to close, depolarizing the cell. So then you've got another action potential. So, and then we've got vision, which we talked about earlier, and that's kind of a recap. We're going to jump to hearing though really quickly. For hearing, this is our lovely ear. You get sound waves that come in and then they hit the tympanic membrane. And this is the line that we cross. We've got the outer ear, middle ear, and then inner ear. So we've got the tympanic membrane, then we've got the incus, malleus, and stapes, and then our cochlea. So what happens is the sound waves travel through this system, and then they match up with the frequency that is triggered within this helicotrema, excuse me. And as we go along, it goes from short to long, and so 20,000 hertz to 20 hertz. And we lose this end a lot quicker than the others. That's why elderly people or people with hearing loss or hearing damage can't hear these really high tones. And then there's the longer ones correlate with low tones. So as we jump further into the ear, we have our lovely diagram here. Scoot forward. The paralymph is 5, so that's both the outside here, and then the endolymph is 150. So we've got these hair cells, outer hair cells, that this tectoral membrane is kind of like jello. So when these are stimulated, they're going to go back and forth, making this move. And then when this moves, it comes down and hits this other hair cell. And that stimulates all of these connections going back to the brain to let you know what you're hearing. We also have the striae vascularis, which secretes potassium. And it is contained within that layer. It can't go outside of that, or else you're going to have some serious problems hearing, like, because you're going to hear those blood vessels and it's going to be loud and miserable. So to blow these hair cells up, the moving triggers the potassium channels. So this one is just a normal one. You can see that we've got the channel and it's got kind of the lid on it, but it connects to the next one. So when these move, it pulls off that cap, allowing these ions to enter into that hair cell. So once again, we're going to jump over here where it's blown up. The inside is positively charged, whereas the outside is negatively charged. And there's that 150 again for the endolymph. And then there's these hair cells. So these have these channels that allow in positive charges to come in. We've got our sodium potassium pump. And then we have a voltage gated, a potassium leak channel. So the potassium can leak out. And then we've got, it's the same thing for each. We just kind of ran out of room in here. Vesicles, and you've got your calcium channels, and then you've got your synaptic cleft that allow the action potentials to proceed to our brain to tell us what we're hearing. So up here, we're blowing things up again. And as you can see, the sound is going to want to work its way inward to the endolymph from the paralymph. So first of all, we have our sodium potassium channels. We've got them right here and right here. And then you've got leak channels that separate these. And then you've got a new channel that we haven't learned about before, and it's the NKCC channels. So this allows sodium, potassium, and 2 chloride ions into the cell. So these come in greatly depolarizing the cell, except you've got this calcium that's bringing it in, so it's balanced out. But you also need, in order to get that action potential forward, you need to let the calcium out of that channel so that you can continue to depolarize. So getting all of these nice calciums, or excuse me, not calcium, potassium buildup in there. And then once again, we have that same NKCC pump, and it just keeps propagating that signal through your hearing so that it can get to your brain and let you know what you're hearing. There you go. Hey, so today we're going to be talking about how the eye focuses light. So to start off, we need to know a little bit of the anatomy of the eye. So here's our lovely eyeball, and you have your cornea, you have your lens, and then there's some key important structures that we need to know for what we're going to do going ahead. So the vitreous humor is what kind of is the gel of the inside of the eye, and holding the lens taut is the ciliary muscles that attach to that. Now there's several different things with the ciliary muscles. When the ciliary muscles contract, they're pulling on these ciliary ligaments, which if you contract the ligaments, then if you contract the muscle, the ligaments slack, and if you if you relax the muscle, the ligaments tighten. So it's kind of an inverse relationship to get that lens to where you want it to be, and we'll discuss a little bit more of that later. We've got blood vessels going through this region, and then you have your optic disc, and then you have your receptors back here, and then your ganglia cells are in here receiving information from the receptors and taking it back to that optic disc and then the optic nerve into the brain. So these ganglia cells right here, this is what they look like a little bit blown up. So there's the cell, and then they're surrounded by pigment epithelium, and that's what gives us our eye color, and that's what absorbs some of the light so that we don't see our blood vessels. Okie dokie, so we have two different types. We have rods and cones. Rods are black and white and distinguish more of the in-depth sight that we see, and then cones are color, so red, green, and blue. And this is kind of a blown up example, so it's actually an alpha helix and the receptors are on the inside of it. So here we have some eyeball examples and different vision problems that people can have. So this is the regular one. You want all of your information, that light bending and gathering at this back point where you've got your optic disc. However, if your eyeball is elongated, it's going to come and hit right here, not where it needs to be, and that's going to cause far-sighted issues, whereas this one is going to cause nearsighted issues because the light is gathering past where the eye even is. And so in order to fix this, you make the lens more convex, and then for this one more concave. So if you're looking far away, it bends less light, whereas if you're looking close, you have to bend the light more. So it's a little bit more work to look closely. So convex, you need to bend the light more, and then flat, you need to bend the light less. And we talked about that. So now we're going to come into the nitty-gritty side of things. So we've got several different things going on here, but we're going to start over here where we've got our retinal, which starts off in a cis, with a cis kink on it, but when light hits that, it straightens. And this is a G protein, so when that happens, you have a conformational shift because you've got your beta, gamma, and alpha subunits connected to that, and it kicks off that alpha subunit, and that alpha subunit comes over and turns on the PDE. Now the PDE breaks down cyclic AMP, and that comes over and it turns off the sodium channel, which is, in this case, it's called DGMP. So that's kind of what's going on at the bottom here. We have our vesicles that, just like the other video we talked about, come and release. So we've got to have that calcium coming in to make the snare proteins bind and then release our glutamate. So this is a voltage-gated calcium channel, and it's opened by the depolarization of losing these sodiums outside of that channel. Okay, so then we come and we have our our synaptic cleft and our junction. And so we've got our first option, we've got MGLUR6, which is the G protein. And so once again, we're going to have that come and bind, the glutamate come and bind to that, and it's going to kick this alpha subunit off, and that comes over and it turns off TRPM1. Now, this is regularly left open, allowing calcium to leave the cell, but since this comes and turns it off, that's going to cause less calcium to leave the cell, and so it's going to hyperpolarize. Okay, so for this one, this is all the same until you reach this part. And instead of your MGLUR6, we have our AMPA. And so what happens here is this is a ligand-gated channel. The glutamate comes in and binds, and allowing this to open, and this just lets any ion come through. And so for our purposes, we're going to talk about sodium is coming through. We also have this voltage-gated sodium channel, so this comes over and knocks this up a bit, causing it to open. And then more sodium can flood in, causing this to depolarize. So we have two different areas within our eye. So we've got the inside, the center, and then we've got the surrounding. So in our diagram that we're going to draw, the black is symbolizing the surrounding, and the red is symbolizing the center. Now the center can either be turned on or off, and the surrounding can be turned on or off, but they're inverse. They can't both be on, they can't both be off. So we're going to see what it looks like when we shine different amounts of light on these different scenarios. So the first one we have is the center is on and the surrounding is off. And if we shine light on the surrounding, it's not going to match up because these like to be in the dark. So this one is not going to be congruent with each other. And this one's not getting light, so it's not going to work. This one is in its happy place though, because it's in the dark, you're not having light on it, and so we're going to have 2 because we work in numbers of 2, 6, and 2. So then for this other one, we've got light on light, so it's a happy camper. This one is dark in the dark, so it's a happy camper, and then this one, not so happy. Okay, so what do we gain from this? First of all, we know that if it's center on and surrounding off, it's going to be an MGLUR. So we're just going to call that MGLU6 because it's quicker. Okay, and that's going to be for all of these. 6. And all of these ones are going to be using our AMPA. Okay, so now we can go to work. So we look at the numbers that we've got here, and we know that we're going to end with 2 because we've been given that number. So our ending number, we know we're going to have 2 action potentials. This one, we know we're going to have 4 action potentials. And so now what we're going to do is we have to calculate what's going on the inside. So let's blow this picture up a bit. Okay, so we're going to describe a little bit before we go into any more depth about this part. So first of all, like our diagram, we have our center and then our 2 surrounding, and then we have these horizontal cells. So what happens is you get a stimulus in these surrounding cells which release glutamate. And that comes and binds to an AMPA channel on this horizontal cell. And then what happens is it causes the release of GABA, which then is going to come and open a chloride channel. Now this chloride has a negative charge associated with it. So when it comes into the cell, it's going to hyperpolarize the cell, making it so an action potential can't go. However, if we shut this off, then we have the necessary calcium to be able to start this whole process of creating an action potential. So having said that, we have some game rules. Wherever light shines, you don't have the release of glutamate. So we've got that first. And then these like to be like. So let's start going through. So like we said, we have 2 right there. So we know we're going to have 2 in the end, and we have 4, so we know we're going to have 4 in the end. So now we got to figure out this middle part. So if we shine light on a dark surrounding, then that means it's not going to go. So then we're going to have this process take place. That means the GABA is being shut off. So overall, you're going to have 2 of these, of 2 glutamate coming from that first one. Now this is turning on GABA, so you're not going to have any coming from here. So you have 2, none, and then this one is not being stimulated, and so you're going to have 6. It's not right. Okay, so actually, we fixed it. So this is going to be a 6 because where we don't have light shining down on it, that means that it can do its job and it can release the glutamate. So this is actually going to be an 8. So that makes sense because these need to be inverse of each other. So now we can work with this. So we're going to start with this side. So this side is not being, well, it's being inhibited. So you're going to get the glutamate. So this side has 2, and then this side you're inhibiting because you have gamma, so you're not going to get any glutamate out of it. And then this one, you're getting 6, so that gives us our 8. Now for this one, it's a little bit trickier because AMPA just allows things through. This one is a little bit different. So since this one is not having the sun shine down on it, it's also going to be a 6. So what happens is you have 2, 6, and you have 8 up here. Now you're probably wondering, how 2, 3, 4, 5, 6, 7. Okay, anyways, how we go from 8 to then 2. Now these are kind of inverse, so we're imagining that you're starting with a 10 amount, and that's kind of just an imaginary number. These are going to cause this to bind, and it shuts it off, and it comes over here shutting that off. So it's going to be inverse. So 8 minus, or 10 minus 8 is that 2, gives us that 2. Now for this one, we have light shining over both of these, so now this can't work. The light is shut off, so we're getting no glutamate out of that. And same thing for this one. We just, if it's shining down on it, we don't. And then this one is a happy camper. This one is not. So this one, we get no glutamate coming out of that. This one's in the dark. It's pretty happy. So it's going to have 2. And then this one is not thrilled because it's not getting light. So it's not getting, so we're going to have 2 coming out of this one. And then, okay, so this one's stimulated, so you're not having any come out of this one. This one is inhibited, so you're having 2 come out of that one. So now we have to figure this out. So because we have 2, and we're back. Okay, so because the light is hitting the on, it likes it, so you've got 6. Now, light hitting on anything that light touches, you can't have glutamate. So anyways, you're going to have none. So you're going to start out with 2. Now, since like we said, this is the inverse, and so you're going to have 8 total, which matches up with what you've got up there. Making sense. Okay, now for this one, we know that we want to end up with 2, which makes sense because, once again, inverse. So for this one, you're just getting the 2 from right here. And it's AMPA, so it shoots right there. Okay, last one, we're almost there. Okay, so this one's not thrilled. This one, happy camper. This one, not thrilled. And then for this one, it's happy camper. Nope, happy camper. Okay, so now we have to figure out what's going on. So anywhere that light touches, not very happy. So for this one, you are having it be inhibitory, so you're going to get 2 out of here and 1 out of here, giving you 4. And then, like we talked about, inverse, now you have 6. action potentials. Now for this one, you are not having these go because they're turning on GABA, and this one is inhibited, so it's turning on 6. So you get 1, 2, 3, 4, 5, 6, and then this one goes straight through. Oh, excuse me, that's not right. This is a common misconception. I'm glad we went here because this is very hard to figure out. You should probably know about it. On this, it may be happy, but it's turning it off. So guess what? That whole thing is now inhibited, meaning that, oh, shabam, you actually have 2 coming in and none right here giving you your 4, which is the actual inverse of 6. And that goes straight through. So watch yourself. It can get tricky. I hope you enjoyed the video.